Okay, so we're going to now switch to a new topic, and that is learning to describe expectation and variance. What is the fundamental idea behind expectation and variance? This is very fundamental to everything we will do in this course. Um, we have performance metrics in reliability, in design context. We have performance metrics, functions, if you will, design functions, if you will, engineering performance measures like stress or expected life of a part, max deflection. Those are all design performance metrics. And because of the uncertainty in geometry or material behavior or load, we find that the performance metric is not a deterministic quantity, but is an uncertain quantity. And that's what we saw in the introduction. And we want to somehow characterize the uncertainty in our performance metric. And throughout this course, we will use two measures of characterization of the two measures to characterize the uncertainty in the performance metric. And those measures are what we would call as expectation and variance. Expectation you can think of as some central value, some value towards which on an average the performance metric tends to, and variance is the dispersion about that value and the average value. We'll define these average and variation about the average more formally in this module. So module 3 is about manipulating expectation and variance. Module 2 was all about probability rules, okay, and learning about condition probability rules such as addition, product rule, addition rule, De Morgan's theorem, and Bayes' theorem, conditional probability. So module 3 is all about expectation and variance. So module 3.1 specifically will define expectation and variance formally, and then we will work through examples in module 3.2. We'll derive some important relations in module 3.2. So what is mean and standard deviation? We've all come across the notion of a mean and standard deviation, and I'm going to define them more formally now. X is a symbol for a random variable. And then we take n random values of x. So we take a sample of n values of x. So x could be, for instance, the dimension of a part. And x is a label for the nominal dimension of the part. And if I take n parts, I might get n random values of the dimension of the part. And those I'm going to denote as x1, x2, x3, and so on till xn. So given these n values, and these are n values out of many, many, many more parts that I produce. So that's why it's a sample. It's a smaller subset of the larger population that I have. So given these n values, now I can define something that I'm going to call as a sample mean and standard deviation. So this is all stuff that we've seen before, like null likelihood. The mean is simply, I'm going to denote it as x bar. Okay, and this is a sample mean. Sample mean is simply x1 plus x2 plus x3 and so on till xn divided by n. So that is the sample mean. That's the definition of sample mean. And similarly, the definition of sample standard deviation, which I'm going to denote as S sub x. The subscript x is to describe the fact that this is the standard deviation of the variable x. That's why subscript x. The standard deviation of x is defined as square root of 1 over n times summation of xi minus x bar squared. So this is x bar. X bar is the value that you calculate here. So always the process would be to first find the mean value and then find the standard deviation using the mean value that we've estimated. Now, if we weren't dealing with a sample of n values of x, and let's say we want to consider the whole population, normally we use a notation mu and sigma to denote the population mean and the population standard deviation. So if as this n tends to the let's say cap n is the population, then this mu would correspond to cap n as opposed to little n, which might correspond to the sample size. And sigma would correspond, instead of s sub x, we would write it as sigma if this were to be the larger population, the whole population. So there are many ways you can describe this measure, what are called measures of central tendency. There are many ways you can describe them. And the one that we would use mostly in this course is mean, which is the definition that we just had, which is defined by this quantity here. This is mean. But there are other measures as well called median, which is defining the value at which you have 50% probability, and mode, which defines the value of the variable at which you have peak probability. Okay, so you could have mean, median, or mode to describe what we would call as a central tendency. So this is what we loosely define as average. In this class, mostly we will use mean, and in one specific case, we will use the median. So these are all measures of central tendency. There's another variable we need to define, that's coefficient of variation. Coefficient of variation denoted as CV with a subscript x to say that this is the coefficient of variation of variable x is the standard deviation divided by the mean value. And the reason for this is we know that the mean has units. This x bar has the same units as x1 through xn. So if x1 through xn were part dimensions measured in millimeter, x bar will also be a mean value measured in millimeters. And the standard deviation of the sample also has units of the same x. So this will also have, if x1, x through x2 and so on are in units of millimeter, the standard deviation would also be in millimeters. And that's because we take the square root of this square. So both standard deviation as well as the mean have, in most problems, physical units. And this coefficient of variation, on the other hand, is a non-dimensional way of describing the spread, if you will, the dispersion, if you will, or the standard deviation relative to the mean. It's a non-dimensional way. So now we are going to define expectation and variance. So far, what we have assumed didn't quite identify. There might be a situation where this probability of a specific value is different from occurrence of x1, may be different from probability of occurrence of x2. So each of these values may have different probabilities of occurrence. Out here, we have not really distinguished that the probability of occurrence of x1 may be different from probability of occurrence of x2, and so on. So now what we are going to do is to say, let's assume that the probability of occurrence of xi is pi, okay, and probability of occurrence of, therefore, now we can, what we're going to define is something that we call as the expected value. The expected value of x, denoted as E of x, and that's x bar, is summation of xi times pi. The value xi has a probability pi of occurring. The value of x being xi has a probability of pi. And the summation of xi times pi is what we are going to define as the expected value. And now we are allowing each of these variables to have different probability of occurrence. And similarly, we're going to define variance of x, again as a measure of spread, if you will, is standard deviation squared. Okay, that's going to be the expected value of xi minus x bar squared. And the expected value of any quantity is that quantity times its probability pi. Okay, any quantity xi, depending on xi, is that quantity times the probability pi summed. And that's the definition of expected value. So if the quantity is x, then the probability of the expected value of x is xi times pi. If the quantity is xi minus x bar squared, then its expected value is xi minus x bar whole squared times pi, and that quantity we're going to define as variance. Now, if the probabilities of occurrence of any value xi is every value of xi is equal, that is, if pi were to be 1 over n, then we find that we can recover the formula that we normally use for the mean and the standard deviation. If all the pi's are equal to 1 over n, expected value of x is xi times 1 over n summed, and that's 1 over n times summation of xi, which is the standard formula for the mean. So that's a special case of the more general definition of the expected value. So again, the expected value is a measure of central tendency because it's the mean, it's a measure of central tendency. And the variance of x, again, if the pi were all equal, if the probability of occurrence of any value xi is equal to 1 over n, then the variance of n gives you the expression for square of the sample standard deviation. And that's what we're going to call as variance. If I have a sample out of a larger population, so my sample is out of a larger population, and I want to estimate the population variance given the sample, then it turns out the formula that we would use would be 1 over n minus 1. And remember, sigma corresponds to population and standard deviation, whereas S sub x corresponds to sample standard deviation. And if I want to estimate the population variance given the sample, then I would divide by 1 over n minus 1, divide by n minus 1 instead of n. And we will do this more formally. We will derive this later on. As an example, we will derive this. So far, we've looked at x being a random variable and x taking discrete values, x1, x2, etc., discrete values. What if x were to have a continuous variation, for instance, thickness of a sheet? There are infinite number of points on a sheet, and at every point I might have a different thickness. So then I have a continuous variable. How do I define the uncertainty of such a variable? And what we do is to take the limit of discrete values. In the limit gives me a continuous function. That's the idea that we're going to use. And we're going to define that quantity as something called the probability density function, or PDF. Let's say, going back to that example that I gave of a sheet whose thicknesses at various points may be different. So what I do is I measure at certain number of points, and then I bin the number of points at which the thickness is. So I bin the thicknesses, let's say, as an example. Then depending on the bin size that I use, one set of locations might give you a distribution that looks like this. Another set of locations might give you a distribution that looks like this. But if I were to bin them even finer, say half the value, then it starts to look like this. And if I make it even finer, bin them even finer, then I would get something that looks like a continuous function. And that continuous function is what we call as a probability density function, a PDF, a probability density function, or PDF. Okay, so the probability density function f of x is of a continuous random variable x, is a function with the property that probability of a less than x less than b, that is, x lying between a and b, is integral of f of x dx between the limits of a and b. So the probability that x would lie between a and b is integral of f of x, the PDF, a and b. So as a trivial case, what's the probability that the x value would lie between x and x plus dx? And that's just going to be f of x dx. So the probability f of x by itself is probability divided by some length dimension dx, so that's why it's probability density. And an incremental probability that x would lie between x and x plus dx would be f of x dx, and the probability by extension that it would lie between a and b is integral of f of x dx between a and b. Now, similarly, we can ask the question, what's the probability that x would lie between minus infinity and plus infinity? And we know the probability that x would lie between minus infinity and plus infinity is 1. X has to take a value between minus infinity and plus infinity, and that has to equal 1. So that in turn gives an important property of the probability density function, that its integral has to sum to 1. Integral has to equal 1 between the limits of minus infinity and plus infinity. An example of PDF is one that we recognize readily as the bell curve or the normal distribution or the Gaussian distribution, as we will learn later. And that has a form that looks like this. Most of the time, we never directly manipulate this form. Then we usually, because the form is complicated to manipulate by hand, so we usually rely on calculators to tell us what these values are. But this is an example of this is an example of a probability density function. So now we can define the expected value and variance of a continuous random variable. Let's say x is a continuous random variable, thickness of a sheet, as I mentioned. And let's say x has a probability density function of f of x. Okay. Then the expected value of x is defined. This is a definition. And remember, expected value is the mean value, right, which we denote as x bar, is integral going from minus infinity to plus infinity x times f of x dx. Okay. And if you think of f of x dx as the probability mass that we had before, okay, f of x dx, and then if you replace the integral by a summation, we would recover our formula for discrete values of the random variable x. And here x is a continuous random variable. Therefore, instead of summation, we have integral, and where we had probability pi before, now we replace it with f of x dx, f of x being the probability density function. In the same way, variance of x is integral going from minus infinity to plus infinity. Again, this is the definition of expected value of x minus expected value of x whole squared. And expected value of x is the mean value, right? So this is the definition of expected value of x minus x bar the whole squared. And that's x minus e of x squared times the PDF integrated between the limits of minus infinity and plus infinity. So again, expected value of any quantity is a quantity times the PDF integrated between the limits of minus infinity to plus infinity. Expected value of x is x times the PDF integrated between the limits of minus infinity and plus infinity. Expected value of x minus x bar squared is x minus x bar squared integrated between the times PDF integrated between the limits of minus infinity to plus infinity. Okay, so that concludes the definitions of expected value and variance of both discrete random variables as well as continuous random variables. So I'm going to stop there with this module, and in the next module I'll derive some special relationships associated with expected value and variance, provide more insight into what these expected value and variance represent.